Okay, so the parallel axis theorem is a very useful theorem once you know the rotational inertias of a few basic shapes, such as a rod or maybe a ring, a disc, a sphere. But those were values all through their individual respective centers of mass. You will not know what if you were rotating a rod instead of through an endpoint or the center. How about rotating that rod around 1/4 of the way from one end? What is the rotational inertia of that? Right? What about rotating a ring not around the center but around the rim? Right? So these are all valid questions, and with parallel axis theorem we can easily calculate these. So first let's get something that we know already. So we'll draw this shape here. So this is the rod rotating around this axis, and the center mass is right here because this is a uniform rod, and we have the length of the rod is L and the mass is M, and we know from previous video that this is ml squared times 112, right? So what if we didn't know the second one? This second one was also in a previous video. This is a rod rotating around its end. So same exact rod, same length and mass. And we were given this value, 1/3 ml squared. Right, I gave some explanations, but that was more or less a qualitative explanation, but not quantitative enough, the 1/3 against 112. So now let's use the parallel axis theorem to solve it. So according to parallel axis theorem, if you have a rotational inertia that you already know through the center of mass, such as this value, right? This is through the center of mass because that is the center of mass. So this is the same as rotational inertia through center of mass. And you want to find the rotational inertia through some other axis of rotation, not center of mass. So that is this point, the axis of rotation, right? So the center of mass is this far. So the new axis is L/2 away from the center of mass axis. Alright, so we want this, we want the new, right? We have the rotational inertia through the center of mass, we want this. All we did was we moved the axis for a distance of, let's call that an R distance. So this is the R distance from the center of mass to another point. We could have just moved maybe half away, right? We could have moved any amount, and that move from the center of mass, the distance is called the R. So how do we get this? According to parallel axis theorem, rotational inertia around any point, if you just move your rotational axis parallel from the axis of rotation to the center of mass, you're actually adding this amount, mr squared. So first of all, mass is positive, r squared is positive, so this I is always equal or greater than the I of center of mass. So as long as you move away from the center of mass, your rotational inertia will increase. Your distribution of mass will cause you to have a larger amount of resistance to rotational acceleration, to torque, and a smaller amount of rotational acceleration. So this is qualitatively speaking. Quantitatively speaking, let's calculate this as an example. So in our example, this R, how much your axis is moved from this old axis through the center of mass. So that's not a 13. Let's get rid of that. Rewrite it. From the center of mass to a different axis that is parallel to this axis. So that R is L/2. You moved from here to the end, half the length L. And the rotational inertia should be equal to I center of mass plus mr squared, that is equal to, the center of mass version is this, 1/12 ml squared, plus mr is L/2 squared, that's a quarter, right? So we have 1/12 plus 1/4 ml squared, and 1/4 is 3/12, so 4/12, 1/3 ml squared. So as a matter of fact, you don't really need to memorize this if you already memorized this and the parallel axis theorem, because you can just move your axis to get over here. So let's do just a quick calculation with just a slight variation. Okay, so now this is the center of mass, and we still have the same exact dimension in L. And here that distance moved L/4. Alright, so we're rotating around this point a quarter of the way from one end. So what is the rotational inertia of this object now? And we have I equals to rotational inertia, so the center of mass 1/12, smallest possible rotational inertia value, plus m, the shift, the parallel shift, L/4 squared. So we have 1/12 plus L/4 squared is 1/16 of an L, ml squared. Okay, we need to find the least common denominator. So 16 has a 4 and 4. This is 4 and 3, so we need a 3. So 16 by 3, 48. And we have a 4, we have a 3, so a 7 ml squared. So now we can answer questions like this all the time. And what if we have a compound shape that has, say, multiple sections, one out of which can be these sections? So let's do an example like that. So now we have a top view for convenience. So we have this rod here, and let's give it L1, and it has mass M1. And we'll just stitch together with another rod, and we'll forget about the diameter of the rod. So we'll just say this is L2, and its mass is M2. So it's kind of a little L shape. Could be an L bracket. So we're going to find the rotational inertia of this thing through whatever point you like to pick. So let's say here, this is that's the center. So let's pick this point. And let's set this to be the origin, so we can get this location is here, this distance. Let's draw this out. L2/3, and this distance L1/2. Okay, so this shape around that center mass. Alright, so first of all, what we need to do is we need to separately look at these two rods. So each rod contributes to the total center of mass, to the rotational inertia. Just like point masses, rotational inertia, they're just adding together. So we find the rotational inertia of this object rotating around this point, and then we find out the rotational inertia of this object rotating around this point, and both using the same exact formula. So let's say I1 is I1 center of mass plus M1, and the amount of movement, let's call it R1 squared, and I2 is I2 center of mass plus M2 R2 squared. So I total is I1 plus I2. Adding these together, that should be easy. So 1/12 m1 L1 squared plus m2 L2 squared. So the center mass versions are the same, except that these values are different. So now they're added together. Then adding m1. So what is r1? So starting from this point, I moved away this much, which is L2 over 3. So L2 over 3 squared plus m2. So what is R2? Okay, R2 is a bit more complicated because R2's center mass is here, L2 over 2. So now it's rotating over here. So this is effectively the R2, and this is effectively the R1. The dashed line is not R2, right? The axis of rotation is here in the center, so it's been moved up L1 over 2, and to the left 1/6 of L2. So this R2 is here. Let's put in L1 over 2 squared, which is the vertical movement, and then the horizontal movement over here. You're going from 1/2 to 1/3. You need 1/6. So plus L2 over 6 squared. Let's put bigger parentheses. So this may take a little while to combine the terms together, but if you had values, you would be able to plug in the values and get a numerical value out. But I'm not interested in that. I'm just showing you with a composite shape, how do you find the rotational inertia of a composite shape through any axis of rotation? Well, you break it down to small pieces, each one of which you already know the rotational inertia through its center mass. And then you move that rotational inertia from the center mass to the new axis of rotation, this axis rotation here. Let's have another example. So let's try to be fancy. Let's get a few things together. So here's a disk. And let's see if I can draw this. Here's a ring. And here's another disk. Okay. I could put some bars together, but I decided maybe not. So this is the axis of rotation. This could be a cool piece of earring if you put a little hook here. So this one, apparently from its look, it has a radius of r. And let's call this mass m1. And this one looks like it has a radius 2r, and it has a mass of m2. And this one again has a radius of r and mass of m1 again. So just 3 pieces and rotating around this. Okay. And let's call this A section, B section, and C section. Okay, so we want a rotational inertia. And we know that it's going to be the sum of the A section, B section, and the C section. And each one of them is not necessarily the rotational inertia around their own center mass. So for example, this. If this is the rotational inertia from this point, so from the A section, we know that this is going to be center mass plus m1. There's going to be a distance, and this distance here. Okay, so starting from here, if this radius is r, then you have 2r here, diameter. Then you have 4 r's here, diameter. Another 2r. But not the whole 2r because you end in the middle, right, center mass here. So we have 2, 6, 7. So it's a 7r squared. And this is going to be, if it's a disk, is 1/2 m1 r squared plus 7 and square is 49, and 1r squared. And off the bat, you can see the difference between these two quantities. So that if you have an object that's several times distance compared to the extent away, and then the shape of the object is almost irrelevant. So half compared to 49, that's about 1% of this, which is due to its distance to this axis rotation. This is treating the whole thing as if it were a point mass located at this 7r away, right? So this tells you how important the distance is compared to the mass. The distance is squared, so it's more important. So this is IA. So this is approximately equal to 49 mr and 1r squared. So let's do IB. So IB, again, I center mass of the ring plus M2, and the distance to the center between these two, so 2r, 4r's. So we have 4r squared. And this is a ring, so we'll have m and the radius squared. The radius is 2r, so it's m and 2r squared plus m and 4r squared. Well, as you can see, it still is more important to be further away from the axis of rotation than to have your own extent of 2r. Right, so this is, you can add them together. Let's also add this together. So 49.5 and 1r squared. This is a 16 and 4 is 20 m2r squared. And then IC is again center of mass m, and its distance from the center of mass to the axis is only an r, and being a disk, it has 1/2 mr squared plus mr squared, which still tells you that the distance to the axis of rotation is more important than the extent of the whole object. So this is 1.5 and 1r squared. So add them together. I'll just put the I here. Just sum all these three values. So 49, 51. So 51 and 1r squared plus 20 m2r squared. Whatever these values are, if you're given numerical values, this is the best time to plug them in, not from the very beginning where you have to plug in the masses and radius of each individual term. Now you only have to do it for these two terms. Thanks.